Somewhere on Earth right now, machines are burning through enough electricity to power a small country permanently, continuously, without stopping. Not to run a factory, not to light a city, to keep a number honest. That number is Bitcoin. And most of the arguments you've heard about it completely miss what's actually happening underneath the price charts and the headlines. People argue about whether it's a currency, a commodity, a bubble, a religion. Almost nobody talks about the one thing that's actually true, provable, and stranger than all of those labels combined. Bitcoin isn't secured by a bank. It isn't secured by a government. It isn't even really secured by code, not in the way most people think. It's secured by physics. Specifically, by the same law that tells you why a broken glass never spontaneously reassembles itself, why heat never flows backward on its own, why time only seems to move in one direction. The second law of thermodynamics. By the end of this video, you're going to understand Bitcoin not as a financial product, but as a machine for converting raw energy into unforgeable, irreversible truth. And once you see it this way, you'll never look at a Bitcoin price chart the same way again. Let's get into it. Before we go further, let's be precise about what we mean, because this word gets thrown around loosely, and loose language is exactly how good ideas turn into empty buzzwords. Thermodynamics, at its core, is the physics of energy, work, and irreversibility. One of its central ideas is entropy, a measure of disorder, and more usefully here, a measure of how hard something is to undo. Some processes are easy to reverse. Melt an ice cube, and with enough energy, you can refreeze the water back into the same rough shape. Other processes are effectively impossible to reverse. Burn a piece of paper, and no reasonable amount of energy will reassemble the ash back into the original page. Bitcoin, it turns out, is deliberately engineered to sit firmly on the second side of that line, the irreversible side. Every part of its design, from how coins get created to how the ledger stays honest, leans directly on the fact that certain physical processes are catastrophically expensive to run backward. That's not a metaphor cooked up for a YouTube script. It's the literal engineering principle the entire system is built on. So let's start where the energy actually gets spent. Here's a number that should genuinely stop you for a second. Each confirmed block added to Bitcoin's ledger represents roughly 10.14 petajoules of thermodynamic work. If that number means nothing to you yet, here's the more human-scale version. That's approximately 2,817 megawatt-hours of real, physical energy, permanently spent, just to seal one block of transactions into history. Now here's the part that turns this from a trivia fact into something profound. That energy isn't stored anywhere. It isn't sitting in a battery you could tap later. It's gone, converted into heat, dispersed into the atmosphere, thermodynamically unrecoverable. And that's the entire point. Because to rewrite that block, to alter history, to change what happened, you wouldn't just need a copy of the data. You'd need to redo that exact amount of energy expenditure from scratch, faster than the rest of the network can keep adding new blocks on top of the honest version. This is why people sometimes call the blockchain a form of thermodynamic write-once memory. Once the energy is spent and the block is buried under enough new blocks, changing history isn't just difficult. It's economically and physically absurd. Let's push this idea one level deeper, because this is where it stops sounding like a clever comparison and starts sounding like an actual law of physics standing guard over your money. If you wanted to double spend a Bitcoin, to secretly reverse a transaction and spend the same coin twice, you wouldn't just need clever code. You would need to recompute all of the hashing work that's happened since that target block, and you'd need to do it faster than the rest of the world's honest miners combined. Think about what that actually means in physical terms. You're not trying to hack a password. You're trying to reverse entropy at scale, to unburn energy that has already been irreversibly converted into heat and dispersed into the environment. The second law of thermodynamics doesn't strictly forbid this in some abstract mathematical sense, but in any practical, real-world sense, it might as well. reversing that much dispersed energy on a global adversarial network faster than new energy keeps pouring in from honest participants isn't just hard. It's the same category of technically not impossible as unscrambling an egg by waiting long enough. Sure, in principle, in any world you'll ever live in. No. Now let's go even deeper, down to one of the strangest, most beautiful results in all of information theory, a principle that sets a hard, physical floor on how efficient Bitcoin mining can ever possibly become. In 1961, physicist Rolf Landauer proved something remarkable. Erasing a single bit of information isn't free, even in a perfect, idealized world. It requires a minimum amount of energy, a tiny amount, roughly 3 times 10 to the negative 21st joules at room temperature, but a real, physically mandatory minimum, not an engineering limitation, a law of the universe. Bitcoin mining today operates enormously far above this theoretical floor. Current hardware is nowhere close to this level of efficiency. But here's why this matters, and why it's not just a footnote. It proves that there is a hard ceiling on how efficient mining hardware can ever become, no matter how many decades of engineering improvements come along. This is the part almost nobody in the crypto debate understands, on either side. Bitcoin's critics say the energy use is the problem, as if better engineering will someday make it disappear. Bitcoin's supporters sometimes imply the same thing, that efficiency gains will eventually make the energy question moot. Landauer's principle says neither is quite right. There is a physical, immovable floor. Bitcoin's security is permanently, unavoidably tethered to real energy expenditure, not because of current technology, because of physics itself. Let's clear up a common misconception, because this one genuinely changes how you should picture what miners are doing all day. People often say miners are solving a math problem. That phrasing makes it sound like there's a clever, elegant solution waiting to be found, like a puzzle with a satisfying unlock. That's not what's happening. Miners are searching for a number, called a nonce, such that when it's combined with the block's data and run through a hash function, the output falls below a specific target value, usually visualized as needing a certain number of leading zeros. There is no algebraic shortcut to find this number, no equation to solve for it directly. The only method that works is brute force. Try a number, hash it, check if it's low enough, and if not, try the next number. Over and over, trillions of times per second across the entire network. The hash function doing this work is called SHA-256, and it's worth appreciating just how deliberately scrambled it is. Each block of data gets run through 64 rounds of bit rotations, logical shifts, and XOR operations. Deterministic, meaning the same input always produces the same output, but practically irreversible, meaning there's no way to work backward from the output to figure out the input without simply trying inputs until you get lucky. This is the physics-flavored heart of the entire system, an operation that's trivially easy to verify once you have the answer, but astronomically expensive to search for in the first place. That asymmetry, cheap to check, expensive to find, is the engine underneath everything else we're talking about today. Here's a detail that deserves far more appreciation than it usually gets, because it's genuinely elegant systems engineering. Bitcoin doesn't just let mining difficulty do whatever it wants. Every 2016 blocks, roughly every 2 weeks, the network automatically recalibrates how hard that brute force search needs to be, specifically so that blocks keep arriving at an average of 10 minutes apart, regardless of how much total computing power has joined or left the network. If millions of new machines suddenly join the network, blocks would start arriving faster than 10 minutes, so the difficulty automatically rises to compensate. If miners suddenly leave, difficulty automatically falls. It's a self-regulating thermostat, constantly adjusting itself to hold one variable steady, using nothing but the network's own recent performance as feedback. And there's a clean formula hiding underneath all of this. If the current difficulty is represented by d, the expected number of hashes a miner needs to try before finding a valid block comes out to roughly d multiplied by 2 to the power of 32. That number isn't arbitrary. It comes directly from the mathematical structure, hard-coded into Bitcoin's minimum threshold values. The reason this matters isn't just technical elegance. It's that this thermostat is what keeps Bitcoin's issuance rate, how quickly new coins enter circulation, predictable and stable decade after decade, without a single human being making that decision in real time. Here's a fact that surprises even people who think they know Bitcoin well. The famous 21 million coins, forever, figure repeated constantly as Bitcoin's defining feature isn't actually precise. Because of how the halving schedule interacts with integer arithmetic in the code, rewards eventually round down to zero around block 6.93 million, roughly the year 2140. The real final total lands at 20,999,999.9769 Bitcoin. 21 million is the clean, marketable, rounded version of the story. The real number is stranger and more specific, a side effect of code, not a decision anyone made. And there's an even stranger detail buried in block 0, the very first block ever created. Its 50 Bitcoin mining reward is permanently, deliberately unspendable by the protocol itself. That energy was genuinely spent. Real electricity, really converted into real computational work. But those specific coins can never move, never be transacted forever. It's a thermodynamic monument, proof of energy expended, frozen in place, that can never be spent. A permanent, unmovable record of the system's irreversible starting point. Let's connect this back to Landauer's principle from earlier, because this is where the theory becomes an unavoidable, permanent feature of the entire system. Even with flawless engineering, chips built with theoretically perfect efficiency, decades from now, mining hardware can never beat Landauer's limit per bit operation. It's not an engineering target waiting to be hit. It's a mathematical floor built into the structure of information itself. What this means practically is something worth sitting with. Bitcoin's energy use can never drop to zero. Not with better chips, not with better algorithms. Its security is permanently, physically tethered to real energy expenditure, because the entire security model depends on that energy being genuinely, irreversibly spent. This is precisely why the phrase in our title isn't just wordplay. Thermodynamics isn't dressed up as a metaphor for Bitcoin. Bitcoin is thermodynamics, wearing the costume of a monetary system. Strip away the price charts, the exchanges, the wallets, and what's left underneath is a machine whose entire security model is a direct, unavoidable application of the laws of physics. Now let's shift from security to value, because there are two strange mathematical patterns hiding in Bitcoin's price history that deserve far more attention than they usually get. The first is Metcalfe's law, the old idea, originally from telecommunications, that a network's value grows roughly with the square of its number of users. Empirical studies looking at Bitcoin's market value against its user adoption have found a surprisingly strong fit to this relationship, with correlation coefficients between roughly 0.8 and 0.9 across long time periods. That's a strong statistical relationship, suggesting network effects. Simply having more people using the system may drive as much of Bitcoin's value as pure scarcity does. The second pattern is even stranger, and it should sound familiar if you watched our video on market crashes and universal physics equations. Bitcoin's long-term price appears to follow a power law over time, with the exponent landing somewhere around 5.5 to 5.8, and a correlation above 0.95 on logarithmic scales. A power law relationship like this hints at a self-similar scaling process underneath the price. The same kind of structure physicists find in earthquake magnitudes, city population distributions, and yes, the critical phenomena we explored in our crash video. This doesn't mean Bitcoin's price is predictable day to day, but it does suggest that whatever is driving its long-term trajectory isn't pure, structureless randomness. There's a shape to it, one more piece of evidence that the physics framing here isn't just poetic license. Here's a fact that deserves to be far more famous than it currently is. Bitcoin's security doesn't just rest on brute force energy expenditure. It also rests on game theory, specifically, on a stable Nash equilibrium that has held unbroken for over 16 years. A so-called 51% attack would require controlling a majority of the network's total mining power, long enough to rewrite recent transaction history. In theory, this is possible. In 16-plus years of Bitcoin's existence, it has never successfully happened on the main chain. Game theory explains why. Attacking the network is enormously costly. You need to acquire and run a majority of global mining hardware, and enormously risky, since a successful attack would likely crash the very asset you're attacking, destroying the value of whatever you gained. Meanwhile, honest mining offers steady, predictable, ongoing rewards with far less risk. Rational actors, computing their own self-interest, consistently land on the same conclusion: cooperate rather than attack. That's a genuine Nash equilibrium, a stable state where no participant can improve their outcome by unilaterally deviating from honest behavior, holding steady across 16 years, billions of dollars of value, and constantly shifting incentives. That's not an accident. That's the system working exactly as designed. Let's be balanced here, because a channel built on respecting real physics doesn't get to ignore inconvenient physics when it shows up. Most conversations about Bitcoin's energy use focus narrowly on electricity consumption. But there's a second, quieter cost that almost never makes it into the cost per transaction estimates you see cited: hardware. Mining rigs are highly specialized machines, and as network difficulty rises, older hardware becomes economically obsolete remarkably quickly. That obsolescence creates a steady stream of electronic waste, specialized chips with essentially no purpose outside of Bitcoin mining, discarded as newer, more efficient hardware takes over. This is a real cost. It's an environmental cost, and it's an economic cost baked into every generation of mining hardware that gets built, used intensely, and then discarded. Any honest accounting of what Bitcoin actually costs to run has to include this, not just the electricity bill, but the physical hardware graveyard sitting underneath the entire system. Here's one of the strangest, newest ideas in this entire body of research, genuinely fresh territory that most finance content hasn't caught up to yet. Researchers have recently proposed defining something called economic temperature for Bitcoin, built directly on Landauer's principle. Essentially, the monetary price paid per irreversibly processed bit of information, measured through the network's transaction fee market. And here's the genuinely strange part: this economic temperature doesn't behave randomly. It shows thermodynamic-style patterns. Specifically, it tends to mean revert, drifting back toward a stable average on a cycle of roughly 21 days. Think about what that implies. Bitcoin's fee market, the price people pay to get their transactions processed quickly, behaves less like an arbitrary market price and more like a physical system seeking equilibrium, the same way a heated object gradually cools back toward room temperature. This is genuinely new, active research territory. But it's a striking example of just how deep the thermodynamic framing goes, not just as a metaphor for the big picture, but showing up in the fine-grained, day-to-day mechanics of how the network actually behaves. Before we wrap up, 3 quick facts that didn't fit neatly into a section of their own, but are too strange to leave out. First, Satoshi Nakamoto's original stash, roughly 1.1 million Bitcoin mined in the network's earliest days, remains completely untouched to this day, sitting there, unmoved for over a decade. Economists studying the network sometimes refer to it as a kind of economic dark matter, mass that clearly exists, clearly influences the system, but has never been directly observed in motion. Second, Bitcoin is arguably the first monetary system in human history whose scarcity is enforced by physics and mathematics, rather than by geology or by government decree. Gold is scarce because of what's buried in the Earth's crust. Fiat currency is scarce because a central authority decides to make it so. Bitcoin is scarce because of energy expenditure and cryptographic proof, a genuinely new category of scarcity that didn't exist before this system was invented. Third, and maybe the most quietly profound, the cost to rewrite Bitcoin's history doesn't stay fixed. As more miners join the network and difficulty rises over time, the energy required to alter any past block keeps climbing right along with it. Bitcoin doesn't just start out secure and stay that way. It gets more thermodynamically heavy, block by block, year by year, history becoming more and more expensive to unmake as time goes on. So here's what I want you to actually walk away with today. Bitcoin's real innovation was never really about currency, in the way we normally think about that word. Its real innovation was finding a way to convert real, physical, irreversible energy expenditure directly into digital, verifiable, unforgeable truth. Every argument about Bitcoin's price, its volatility, its future, all of that sits on top of a foundation that has nothing to do with speculation and everything to do with the second law of thermodynamics. You cannot argue your way around entropy. You cannot regulate your way around Landauer's limit. You cannot outnegotiate a Nash equilibrium that's held stable for 16 years through sheer, cold, mathematical self-interest. That's not a claim about whether Bitcoin is a good investment. That's an entirely separate question and a much more uncertain one. This is a narrower, more defensible claim. The security underneath the price chart is real physics, not a story someone made up. Whatever you believe about where the price goes next, the thermodynamics holding the ledger honest isn't up for debate. It's just how energy and entropy actually work. Gold gets its scarcity from geology. Dollars get their scarcity from decree. Bitcoin gets its scarcity from energy, entropy, and math, the first monetary system in human history secured directly by the laws of physics themselves. That's not hype. That's thermodynamics, wearing a costume nobody bothered to look underneath. If this kind of thinking, where physics quietly explains the parts of finance nobody else is willing to explain, is why you're here, subscribe. New videos every week, breaking down the hidden math behind money. See you in the next one.